I took the session on Tuesday. Yeah. Yeah. So we were discussing about and also I, I, I almost finished the summary kind of on week 5, and we talk about the exponential. We have, we had talked about the exponential function there, and which is this week 6 is, you can say, a sequential part of week 5. Uh, the main is week 5. The week 6 is just uh, like one part of the exponential. Once you know that, okay, the first thing is what is the exponential. So exponential is writing in kind of where a to the power x, where a is a base called base and x is in power, and there is one constraint on this function that a should be less than or equal to 0. In the standard form we are saying, just
Sir, cannot hear you.
yeah, I just muted because some background noises coming. Okay, so there is some constant on the base, which is this one, and it should be greater than this one, where a is belongs to r. You can not r in this range now. In this pattern, where a is a real number, you can say. In this fashion, the function is defined. The reason is giving to the constraint. Some constant is like why we cannot take negative, as x is a real number. X can be any real number. This is from R. So if it is a is negative and thinking like this, suppose a is -1 and x is, you want to find the value, like you want to find at 1/2 where a is -1. So this is going to be kind of this one, and this is not a real number, it's a complex number. There is no mean to ask the root of -1. So that's why the complex also arised. Complex number are also, like, after thinking, the first thing is the natural number have arised, then integers have, then slowly rational. After integers, the directly real numbers came. In between, the rational and irrational came. So then after the complex number came, when we are like started the mathematician as the root of some positive number, then I started thinking what is going to be the root of negative number. Then the complex number came. So that's why this function is this kind of function is not the base is not negative. So already we have seen that this exponential kind of function is 1 1. We have very, in the brief way, we have seen last session, which I have taken. We gone through the horizontal line test, which is actually, once you know the graph of a function. So knowing to the graph of a function, if you draw the vertical lines and which will intersect only one point, that's fine. If it is intersecting, sorry, not horizontally, it is intersecting more than 2 points to the graph of the function, then that function is not 1 1. And and there is one vertical line test that is decide to uh, if a relation is a function or not. So as exponential function is actually an increasing function, and if it is a function in increasing, so directly you can say that function is 1 1. So this exponential, for any, whatever the constraints are here, for any case, for this case only, if it is a is in between this form, then function is decreasing, and if it is in this, if a is in this from here, a is greater than 1, then in that case function is increasing. And in both the cases, if it is increasing or decreasing, so once a function is increasing or decreasing, in that case the function is going to be 1 1. So once a function is 1 1, then we can talk about the existence of inverse of that function. So that's from here, once we have exponential and it is 1 1, and we can talk about the inverse of a function. That's why the logarithmic of a function, like logarithmic of a number, is came, because as you give, let's say a is equal to 2, and then that the function is going to be 2 power x. Okay, and suppose f of 4 we want, so it would be 2 to the power 4, which is 16. So as this is one function, so suppose this condition is given, fx is equal to 16 is given, or you can say 2 power x is equal to 16 is given. So as function is 1 1, so we can find the pre-image of that pre-image of this one. So what is going mean to say, what is going to be now x, how we'll find x? So that's why once we talking about the how to find x, so log is came and log is like constructed, how we'll find that. The best process is either you can think it like this, 2 or 4, and you can compare these two and x is going to be 4, or can take the log both side. So we'll tell you what is log. So that's why the log function is now, you can think, so log, this is f of x, and this is going to be, mean both side means from here you can take, so this is going to be log with base 10 or base 2, even base 2 you can think. So this is 2 sorry, so from here this portion will give x, sorry, log base 2 to x, and log base 2 16. This is, so some log function have some property, we'll see slowly. So it will send the power to in the multiplication, so it would be x time log 2 is equal to log, this is 2 and 2 to the power 4, then again this 4 will come here, so this is x, and this log with base a and the value of the log at the same point would be 1. So as you can see here, okay, we'll discuss more. So that this is the property here, so this is going to be 1, and this is again going to be 4 times 1, so this implies x is equal to 4. That's two process. So the reason is log is an inverse function of exponential. So suppose we have exponential this function, so inverse of this exponential, inverse function of this exponential function is gx, which is log base 2 with fx. Sorry, this is x here. This is going to be the inverse function. If you are already, we know the composition, so you can think f circle g, you can see that slowly. So this is going to be f gx. So f time value of the function at this one, so this is 2 to the 2 to the power log 2x. So in this case, one property of the log will now apply, will all properties see. So this is x. Similarly, g circle f we can think, and here again the log property will come and tell that okay. So that's why the inverse of this exponential is actually is log base 2x. So let me go with the lecture wise. So in this lecture, sir is telling about log. Okay, so So finally, you can, so this I just given, these are just examples. So if you have a function fx is equal to a to the power x, where a is just in formal way, I'm explaining it. So if you have this kind of exponential, then we can talk about the inverse of this exponential, which is a logarithmic function. And here you can say gx is going to be your log with a base a x. And again, the same constraints you can think a is equal to, the same constraints are here will follow. A cannot be negative, and you cannot take a as 1 and not even 0. So, and a should be, either a should be greater than, the same constraint will follow, because in this constraint we are talking about the function. So same constraint will follow for the inverse of the function. So this is logarithmic. This is called logarithmic. So it has some property. This property will infer from the directly this from the exponential itself. So for the time being, let's say we have this function. Okay. Let me tell you the examples. Let me tell you the properties of the log now. The first thing is log. And see, these are the, you want to find the value at a particular point. Let's say you want to find the log 5. Sorry, value of the function f5. This is cx, sorry. g5 equal to log a5. So assume that a is, if a is 2 here, as here for the case, so that means you want to find the value of log 2 5. So if it is these cases, so there are some property based on that we will do. So see, already see how we will find this value. There is already given a table, or from the calculator, from the TCS calculator, if you are in which, or even in Desmos, just give the value itself, this function, give this number, then it will give the rational number, or whatever the number value is there in the form of real, it will give you. So already log is kind of like, you know, sine, cos, theta, the fixed values. Sine 0 is 0, sine in trigonometric, sine 90 is 1, sine 45 degrees 1 upon root 2. So similarly, log with base 2 5 is some have value. It have some table, it already given in calculator, or either in the form of in a big book already you have seen, like in the log sine values or trigonometric values given there, the log values also used to written. So some properties are here, like if you have base a and this is b plus log with base a and c. Oh, I am missing something, maybe log a b c. So this could be written as log a, sorry, base a b plus log a base c, sorry, log base a c. And another property, see these are all came from the exponential. You can infer that how we can find this, how it's came. You can assume, like you want to find this expression. So this a b x, sorry, bc is equal to, assume a x value. Now this could be written as, so one thing I am missing to say, once you have this kind of expression, so this will come to the power here and this will go here. So that means this will come as a to the power x b c. This is the mean to say generally. Okay. Yeah. So I think I'm missing something.
Sir, a to the power x should be log bc.
No, not log bc, this person. This person. This is correct. This is fine. This is a usual. Now, if it is in this fashion, the mean to say, if you have log base a b is equal to am, let's say small m is here. then that means a to the power m is equal to p. And if you have a to the power, let's say n is equal to c, if you want to change it in log, so that means it will be base a and this c here. So power value come to equal to it. This is the mean. So this is if and only if condition, you can say here is both side will. If it in this fashion, this will come. If it is in this fashion, in this fashion it is written, so this will come. That's the mean. To the exponential to log and log to exponential. It's the process to change it.
Yeah, okay.
Okay. I think I'm missing something to prove it. Let's say. So that means here text here. Now, if you want to prove, suppose this is log a, bc is equal to m, not this one. Okay, so this should be a to the power m is equal to bc. This is the left side. Okay, now we'll take this one, log ab plus log ac equal to m. Then we can take the power, this number as a power to the power a to the power this number, log ab plus log ac equal to a to the power m. This is the left side, and we reach to this number, a to the power m is equal to bc. Now let's take right hand side, and this is, after doing this, we took the whole number to the as power of a. So now think about, so this is as it is. Now think, you know that if a to the power m plus n is here, then that means a to the power m into a to the power n is this, use the property of the exponential. We can use it here. So this would be a to the power log ap plus a to the power again log ac, and this is a to the power m. Now, before to proceed or before to prove this one, that means here, if it is this kind of, directly you will get, no, it is multiplication here will come. Yeah. So directly this means that this is b and this is c here, a to the power m. So again, bc is equal to a to the power m. So before to, we need to prove this one. How a to the power a base a b is equal to b is coming. Once we'll prove, we will done. So that means here, see that the same equation here, same equation here. That means this equality is actually true. That means if you have such kind of, then you can, if it is in this fashion is written, you can write like this. And how we will get this one? If once we prove, then our proof will done. So how we'll get this one? So a log a b, let's assume n. Okay, then what we can do here, we have to use again some property of log. I think I'm missing. We can take log here as the log says. So log a log ab is equal to n. So as it is a power of some that base, and here is, so you can send it ab, and this is log aa is equal to here log an. So this values will go 1. That means here log ab is equal to log an. Now, as logarithmic function is increasing, it is logarithmic function is also 1 1. We'll see that. We need to see the graph of it. So this is going to be now as it is 1 1, so that means this b is exactly n. So that's here n is equal to b. That means here is actually will b. So once you prove this one, then everything is fine. So I'm leaving the other proofs, other property, proof of other property. That's the process you can to prove it, use to prove. So the another property, the second property is of the log is a, if it is in the divided form of two number. So this could be written as log m minus log a n. And as once already we have proved this property, a to the power log base a b is equal to b here. And I think the fourth property.
Sorry to interrupt you, sir. Sir, can you please explain that first one again? So before that, yeah, this one, sir.
So
So
take
much
the right.
confusing. I am even not getting like, sir, this is like in the right side, you write a to the power log a is the base and b is the number, right? Log b, right? With the base a, correct?
Yes.
And then, sir, can you scroll down a little bit? And then,
Okay.
sir, you made in the right side, you write log to the power log.
Yeah, log to the, not log to the power log,
So
a
what
to
is
the
this?
power log, a to the power log base ab plus the whole. This is the a to the power the
But
whole
sir, how
expression.
this one has come? I'm not getting. So right side, which you write now.
Just assume that if you are assuming this is equal to some number a, so take here exponential. Take here the log both. Sorry, a to the power log both side. I
But sir,
am
we
here
haven't
taking.
take both the side. We took it at one side only, left hand side only.
No,
right?
no. Here is assuming. See, I just assume this is a number. Okay, I assume this is a number. Also, here is left or right because of I wrote left and right. Maybe because of that you people got confused. So directly need to prove. Okay, I think I have missed. I need to arrange is the number because this is a number. I assume this. So that's why I reached to the same equation, or directly this process will be good too. I think I made not a, this is not a mistake. It's could be, it is some kind of confusing because left and right I have just written, because of that it is confusing. So directly let me write here. If it is a b c is equal to, that is that proof is not wrong. Because I think I told you in the left and right form, that's why you got confused. So here is the best thing, a and this is b plus this is a c here. Now take here both side, assume this is true. Okay, no, just a minute. We want to prove it this one. Okay, we want to prove this, is this expression is correct or not. So so not here the left and right part. Okay, just assume. Okay, the process is how we will prove the left and right part. We will take a left part and reach to the right part. This is the process. So now you can take log a b this. Let's assume here rem. That's why I took here rem. Okay. Now what we can do? So no. So here, that's why I take the right side. Let's say right side, and assume this equation, right side of the equation. Assume this is equal to some number. Log a b plus log ac. Let's assume this is a number. Okay. Now we can take the power of the same number. So this is going to be a to the power. Both side take as power of a, b plus ac. It's going to be a to the power m. Now we can use the power adding of two numbers. So this is going to be a log a b and into log a. This is, sorry, here is a log ac. This is a to the power m. Implies, now we have already proved this one, how it is one, how it is going to be b. So B into, again, this is going to be C equal to AM. That means, yeah. Okay, that is A to the power M is equal to BC. Now, if you have any expression in the power of, we can change in the log form. So that means log base A BC is equal to M. So actually this number M is, we assume this number is, this expression is M, and we find finally the M is actually this log. That means the final thing is, you can write log A B plus log. That means you finally, your this expression is true, right? As this number you assumed M, and finally found this number is actually this one. That means this is equal to this. Is it, are you getting all of you?
Yes, sir. This part I got it.
Yeah, so this is the process. Like, take this right side, or anyone, assume this is a number which is M, and we arrange, or we did some manipulation or arranging the terms, and we finally got that this number is actually can be written in this fashion also. So that means this is equal to this. Sorry, that means this is equal to this. That's here. Fine.
Yes, sir.
Okay. So,
Sir, is
and
that the same which you prove, like N is equal to B? Is it the same thing? So because
N
this
equal to,
part, yeah, here, just above, yeah, here, sir.
this is, I proved for why it is why this is happening, why this is true.
Okay.
This part I proved here, and I used this part here to proving this. Here a to the power log with base a b is already given. So this is going to be now a, and here base a is, so it will be b. A, and here is base a is, so it will be c directly in multiplication, and the right side is already going as it is. Okay.
Yes, sir.
Okay. Now another property is, let's say a to the power n and b is there. So this is equal to 1 by n log a b. This is one property. I think that's all. There are 4 property. Let me see once. One thing, the next property is, the first property itself, a b to the power. If n is there, then it is n log a b. And minus is there. Another property, if you want, this is one form of a. If it is 1 by b, so this is minus log ab. It is a reason why it is minus. So using this property, we can easily see that here minus 1 by b is actually b to the power minus 1. So whatever you have in this fashion, whatever the minus is here you got, so minus again, as using this property, will go to the in the multiplication, and it will become minus log ab. That's all. 4, 5 property. This is 6 property. These are some property. This property is many time used. You can use many time this property, because some equation, while solving some logarithmic equation or exponential equation, many times you will get such kind of thing. So directly this, if it is a to the power n, you can directly send to the 1 by n log a base ab. So this is a very useful property. This one also. These two are very useful. Okay, so these are the some property. Now, so the next thing is, we whatever we did here for the log, we, before to see this property, there are some property of log function, which is, we can infer from the directly from the graph. So as you know already, the graph of exponential function in the case of a greater than 1, this is increasing function. Okay, this is a and this is f of, sorry, this is x and this is f of x axis. Now, as we discussed that logarithmic is just the inverse of this one, f of x is equal to inverse of this function. So actually the inverse of a function is mean to say, let me tell you, if you have a function fx is equal to, let's say, x cube, so and the graph f x cube is actually already, you know, that this is kind of this one. So can you think, so inverse of this function is what? Inverse of this function is actually gx, and gx is equal to 1 by x to the power 1 by 3. As you can see, f circle g is x, here is f gx, and this is going to be f of x to the power by 3. Sorry, here is 3. This is going to be now x to the power 1 by 3, and this is 3. Now power you can multiply. Now this is going to be 1. So this is x. So inverse of this function is actually this one. If you see the graph of x to the power 1 by 3 cubic root, so this is going to be this one. Am I right? Yeah, I think this is correct. Yes. So root of this is the graph of this gx, x to the power 1 by 3. Or if you have a function fx is equal to x square, so graph of x square is this one. Okay, so this function is not 1 if you think x is in the portion of this. So in this portion, the graph of the x square is this one. In this portion, it is 1 in this interval. This x square is. So in this portion, you can invert. You can find the inverse of this function. So inverse of this function is actually gx, which is positive root of that number. Okay, inverse of this function is gx, which is root over x. And the graph of this function is actually this one. This is the positive portion, you can think. So these are some, so why I am making it, if you see that there is a symmetricity is happening each time with respect to the line y is equal to x. It is not correct. If you see that there is a symmetricity is happening, the graph of is actually of inverse function is actually symmetric with respect to the line y is equal to x. This is happening. For the, here is, we can say better way, that this one is y is equal to line x. So how it is going far with respect to this line, you can say the inverse of inverse function graph, which is root over x, is same. It is going far, but this side. So in one graph, you can say if it is a graph of x square, this one, and this is the line y is equal to x. This is the graph of x square in the portion of positive side. So graph of inverse function is actually this one. So see that it is a symmetricity is happening with respect to this line, as this is y is equal to, as if you compare how the graph is going with respect to this one, there's a very similar or exactly symmetric is happening. How far this one, how far this one, how far this one, how far this one. So there is a symmetricity is happening with respect to the line y is equal to x. So this is graph of root over x. Similarly, for cube, you can See, if you have a function fx is equal to x to the power cube, just now we created already. See, this is the graph of x cube. So if you inverse is actually x to the power 1/3. So if you see the graph, it is going to be like this. So if you see that there is a symmetricity is happening with respect to the line y is equal to x.
Sir,
Yeah.
sir, as we do the inverse of function, I noticed that I think end behavior do not change here of
Yeah, end behavior is not
both the graph.
yeah, both the graph.
Uh, is it? It happens all the time.
Yeah, the end behavior is will not change, but yeah, if you think about the inverse, so it will come some constraint again. Sometime the positive side is exist, but negative side is not exist of the end behavior, as the negative side of the function is not even you can talk as for this one, for the x square itself. If you see the for the x square finally, if you think about whole over x over real function, we only talk about the root over in the positive side. So that's why in the some portion in the behavior in the positive side you are able to see, but negative side you are not able to see. So it is not always true, but yeah, if it is happening, then yeah, in the behavior in both side very similarly you can see there. Okay.
Yes, yes. Okay, sir.
So this is, if you see that this is the cube here, and this is happening. How far this value with respect to this line, so that much for this value will happen. Okay. So this is the symmetricity. So why I am making this? Actually, when we talk about the inverse, so we already talked about the exponential, and inverse of the exponential is this one. So there is a very similarity. If a is greater than 1, in that case, okay, just a minute. So we already seen that the graph of a to the power x is where a is greater than 1, this one. So how we can draw the graph of the logarithmic function, inverse function? How the graph will go of the log function where a is greater than 1, base a is greater than 1. So see, let's draw the line, symmetric line, the line which the graph is symmetric. So the graph for a power x is symmetric. Logarithmic is symmetric to the with respect to this line y is equal to x. So this is the line. So see, now be careful here. See this, what is happening here? This is the graph is like this. Okay. Okay. Before to proceed the graph, I think one party I missed that. Okay. When domain of the logarithmic. So I think let me explain you the domain of the logarithmic function. So as you know, the exponential a to the power x, where a is greater than 1 for a particular case, in this case, this value is always positive, a to the power x. Whatever you will take, this is always positive. And already you know the graph of exponential is always lying the positive part of the y-axis in this portion, not in the negative part of the y-axis. In this positive part, it is always lie. So the values of the exponential is always positive. So, and log is, as you know, the log is inverse of the exponential. So that means whatever you will value give here, that should always positive, because logarithmic is inverse of the exponential. So whatever the value come for the image or in the range, that will image will come for the domain of the inverse function. That's the process. You know the relation. I last time I think I missed that. If you have a function fx and gx, and f and g are inverse to each other, so domain, suppose your function is f from domain to range, let's say a to b, and then domain of inverse in function which is g of inverse function of f, which is g here. So domain of inverse function is actually the range function, sorry, range set, which is B, and domain of range is going to be exactly the domain of f, which is A. If it is f and g are inverse to each other, so if f have domain A and range is B, so in that case the inverse function have domain B and range is A. So same is here. As here you are getting exponentials gives always positive number. So that's why the logarithmic use always the positive input. The input for the logarithmic function is always positive real number. Just a minute. Whatever I am discussing, is it clear to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. If you wherever you are not getting, please let me know. Okay. So, so as exponential give the always positive number, it is lying in the positive part. Okay. For see, this line is range side of the exponential, and it is always the, see that graph is lying in the positive part of the range side, which is y axis you can say, or the fx, which is y. Let's say this is y axis. So in the y positive side. So that means what is going to be the input? Only positive number. If you think about now that to graph of a logarithmic, so what it means? It means that whatever input you will take for the log, it should always positive. That means your log input will take from positive side. I don't know what is the graph. Now we'll try to construct a graph of logarithmic. So first thing we know that it takes value from positive side. It will not take the value in negative side. This portion will not come in the as the input of the log. This portion will come. That means graph will lie for this portion only. One thing, and another thing is as logarithmic, see, as here, now need to be careful. Here domain and range. So range of f is going to be the domain of G, and domain of f is going to be the range of. So see, we have a to the power x, our main function. So values here, x take any real number. That means input, that means domain of A is any real number. So output will come of the inverse is actually any real number. That's why one thing is clear that the logarithmic value can be negative, output can be negative, but input is always positive. So two things is clear. So in the quadrant, if you see that input is positive and output can be negative and positive. So in this portion, that means in this portion your graph will lie. Output can be negative and positive both of the logarithmic. As here input of the exponential is negative positive, A can be any real number. So that means output can be any real number. That means is this portion only the logarithmic graph will lie. Two things is clear. This one is always input is positive and in this portion will lie. So this coordinate, this portion, half of the portion of the right side of the y-axis is graph of will lie of the logarithmic. Now, one thing we already seen that symmetricity with respect to y-axis now. Sorry, symmetricity is with respect to the line y is equal to x, this line, which have slope 1. That's the meaning here. This line have slope 1. So let's now make a symmetricity. So as here, this is going to be, this portion is negative side, you are giving the input and getting your output. These are outputs. Okay, and it is
Excuse me, sir.
Am I audible right now?
Yes, sir.
Yes, sir, but
I
cannot
think
see
I-
your screen.
Yeah, let me see here once again. Okay. Now try to let's make a symmetricity with respect to the line. So we know that in this portion, the graph of Ix is lie. So, and one thing I said, our values will be always positive of the whatever the input is going to be positive of the logarithmic. So that means one thing you can say, asymptotes now came here, asymptote already. So always will positive means you can, the value at 0 is not defined. Log a 0 is not defined. That means this is x is equal to 0. You can x is equal to 0 is actually we have like a asymptote. So that means here is it is going to be like this. This is the line y x is equal to 0. That means y axis. So it is we have like asymptote. Okay, and one thing you can from here you can see log, we have function gx is equal to log a, this one. Now if you substitute a is equal x is equal to a, so this is going to be a and this is 1 here. So that means you know one thing, that at the value a it is going to be 1. So let's say a is here, so and a is no one thing, a is here. Okay, and then output is no at a the value is what, 1. Okay, no, it is 0, right? What we know that I am missing something. Yeah,
So
because
log A of A is 1, right?
a of a is 1. I think I am just missing a to the power 0 is 1. Yeah, sorry, this one is 1. Any power of a is 1. Sorry, a to the power, sorry, this we know that log a, this one is 0. In with base any a, and value of 1 is actually 0. As here the reason is you can change this one, you can change as log a1. I was missing that. This I want. That means value at 1 is, sorry, value at 0 is 1.
So, sir, the graph will cut at x-axis where one
So,
coordinates are 1,
uh,
0, right?
so actually at 1 the value is 0. So here is suppose x is equal to 1. So value y value is 0. That means here you can say one root is there. So like this, slowly, and symmetricity is also will help here to how will the graph is. So now this will go like this with respect to this line. Once we know the asymptote, this is going to be asymptote because this is asymptote, this is asymptote. We got value 1 here, so this is going to be like this. As here the graph of exponential is this one, logarithmic in the case of a greater than 1 is this one. So one thing is that as for the log a to the power x, sorry, a base a with x, a is greater than 1. In that case, you can talk about there is no y-intercept, as there is no y-intercept. Actually, y-axis is asymptote. Okay, asymptote. Yeah, it have one root, which is for logarithmic, it have one root, which is x is equal to 1. Root is there. There is x-intercept. Okay. And in the behavior, if you talk about the in the behavior, so in the behavior is as x is going to be positive side, logarithmic is also increasing. So the log values will also increase, but very slow. This will go also positive side. And you can say as x goes to 0, because you don't have 0 value of the function, this one. So you can say if as x goes to 0, logarithmic value is going to minus infinity. This is This is one part from the graph you can conclude. As see that it is going to be 0 this side. If you see that value, very small value you are substituting the logarithmic, the value is going to be very large in negative part. So very small in the second one, very small. So y-axis is going to be as the asymptote. So as x goes to 0 from, you can say, positive side, from this side. So that means your log value is going to be very small number. This one, minus infinity. Is it clear? Is this clear?
Yes, sir.
Okay. And okay. So now talking about the increasing and decreasing. So it is increasing function. You can see that if you substitute very close to 0, it will give very small number. If it is substitute here some value like this, you can compare. As value is increasing, yeah, the value of the output is also increasing, but very slow. So this is an increasing function. So you can say this is 1 also, as it is the inverse of the exponential. So this is 1. So these are some property of the log, and we'll construct the graph slowly. And this is part of when we talk about log base a when a is greater than 1. So similarly, we know the exponential when a is in this portion 0. In this portion, the graph of exponential is like this. So let's make again y-axis, y is equal to x line. This part, I think, like this. This is the thing. Y is equal to, sorry, this line when a is in this portion. Graph of this one is this. Am I audible right now?
Yes, sir.
Am I audible right now?
Yes, sir. Yes.
Yes, sir.
Okay. Now, for the in this case when log is this and a is in this part. So now let's make a symmetricity again. Here this is going to be x-axis and this is here. So how the graph, we already know the when a is greater than this portion is there. So how for the when a is negative, what is going to be in that case? Symmetricity will happen now again. This is our line. I think just a minute. So for the log for positive side is this one when a is greater than 0, and for
So
the case
for-
of
Yeah, so for this, we have to like the y decreases with the increase in x. It should be like that.
Yeah, so yeah, in this case, the as x is increasing, the y will decrease here. So from here we can conclude one by, let's say it slowly because I am not also getting. So let's conclude here how we will construct here. So this is for a to the power x. So as when a is in between, so as a is in x is increasing, the y output is decreasing. The similar case will happen. Okay. So for the case this one, x value will increase. So one thing is clear that this again the input will be always positive for the logarithmic. Okay. And when x will increase, the value also, because of symmetricity, the value will also, in this case, as value is decreasing, the logarithmic is also, the value will decrease. So the graph would be, in this portion will lie. And one thing we know that again y-axis is going to be asymptote. So if it is, see, that side is, this one was going, and we know that value is in that, when a is greater than, it is increasing. So we know that, okay, y-axis is asymptote, it is happening, and value should decrease. So this will happen. The graph for the logarithmic is, for the case of a is less than 1, in this portion will happen. So as we know, the y-axis is again going to be asymptote, and as value will increase, the output, so input will increase, the output will decrease. So here is again happening, the input is this one, so output is this one, so our output is decreasing, and as input is increasing, and the value at 1, it is going to be 0. So graph of, for the case of ax in this portion is going to be this one. So slowly, see, in starting, I also forgot, but one thing I know that, okay, y-axis is going to be asymptote, and as a to the power is, in this case, is decreasing, the same thing will happen with the inverse also. And
Sir,
yeah,
there is no symmetry along the line y equals to x.
no, it is happening, the symmetry is happening. See, we will see this. So this is the symmetricity is happening. Okay. I think, and then I'm missing something. No. Graph is fine. For a to the power x, in the case of, in this portion, the graph is this one. Okay. I think let's see the Desmos symmetricities. I'm not seeing here. Okay, just a minute. Let's say to the power x is this one, and log with base 2 x is, oh, for the, this is for, in the case of, I made this one, this is, let's say, 0.5, and you see again here base is 0.5. So this portion is there, symmetricity is, this is the, we made correct. Okay, I think we are not able to see there. If you draw the line y is x, this is the line here. Okay. So this is going to be our line. I all have drawn y is equal to x, this line, and this is going to be the 0.5 to the power, or you can say 1/2 to the power x, and logarithmic is, the base is 1/2 and x we want to find in that case. And symmetricity is See, this will, all three will pass through the point is here at this point. Okay. Let's see. Slowly we investigate here how the symmetricity will occur here. So our line is this one. This is going to be e to the power x, and this is log base with a. Okay. This is fine. In compare of this line, this y is equal to x. Okay, whatever the values we are getting, so here is input, this one is for output. Exact symmetricity, it is actually, yeah, it is symmetricity is happening. I just made a tir in this fashion, that's why you are not able to see. It is what is happening here. Whenever we compare, see, sorry. So this is the line here. So symmetricity is in compare of this thing is happening. Like here is this one, so here is far. If it is see that this is going to be far, so this is going to be far. Or in a different way, if it is so in the symmetricity in this fashion, this with respect to this line, it is happening. This is going to be far, so this is too far. Okay, this is happening. Or it is the value, see, the whatever the thing is happening here is because of the, it is inversing, like it is in the negative part it is happening, and it is in the positive part. That's why the symmetricity it is look like a different thing, but it is actually happening. So this is, we can see one by one. If it is far is going, this part is far is going, because as this portion is going to be input, right? So this value is here, as input is going and output is going to be too far. So here is also happening. This is going to be too far. One by one it is happening. In this case, it is a symmetricity. No? Yes, no.
Yes, sir. Yes, sir.
And in compare of this one, this is going to be very close, like this is and this one. In this portion, it is happening here and here. This one, it is happening. And here is this, and here is this. Okay, this is happening for the line, this one and this portion. Okay, this is the symmetricity is happening. In the graph, it is actually kind of difficulty here, but this is the symmetricity. Okay.
Okay, sir.
So this is all about the logarithmic, and we have been increasing, decreasing. Now we have seen some properties also, and anything is missing. Let me see once. Now we need to use this log to solve some problem. So for example, I am giving a function, maybe even it belongs to the activity. So suppose we have a function fx is equal to e to the power x minus e to the power minus x. So I think it is some, or in the log we can feel it. In the log, let's say in the log, it is e power x minus e to the power minus x. We have this function. So is this function 1, 1? Is it increasing? Is it decreasing? And anything more? 1, 1, increasing, decreasing is invertible. There are some options. So how we'll check, is this increasing, decreasing, or what's happening here for this function? So how we'll check this? Because this is kind of this one. So how we'll check, is this increasing or decreasing? Anyone, please even try to solve this. How we'll solve this one?
Sir, can we expand this expression as log e to the power x minus log e to the power minus x? Can we do that?
No, this property is not hold for the log, right? This
Okay.
a minus b is not,
So-
you cannot like this. This is not, this is
Okay.
wrong. This is true for log when it in the divisible form. The number m is divided by n, then in that fashion it is going to be. Sorry, this is m here, this is n here. So this will not help.
Okay, okay.
So we can write this as log e to the power x divided by log e to the power minus x.
Log e to the power
X.
divided by log. Yeah, okay, we can do this. No, we cannot do, right? Because this is in here in the log, there is no log, here is not log. So we cannot do this one. So how we'll do now? Anyone? Okay, so let's see how we can do it here. We know about this one, e power. Let's in the part we can think. We know that e power x is increasing. Okay, we know this one, and if this is happening, so what can you tell about e power minus x?
Decreasing, sir.
It is decreasing. It will decrease. Because whatever this one will come in, the input will come this one, like e power x is this one. So e power minus 1, what will be? Sorry, e power minus x, the graph of e power minus 6, exactly e power 1 by x will. Or whatever the here for the, like, see, this value is, if for x value you are getting this one, for positive side this one, so this will like this. Or differently you can think also, this is going to be 1 by e to the whole x. So this is now become less than 1. So graph will be now in this fashion it is happening. So the revertible part will be like this. So actually you can conclude here it is decreasing. In a different part, as you know that when a is greater than 1, a is increasing. When a is in this part, then a to the power 6 is decreasing. So here you can think 1 by e is actually less than 1. No, because e is actually 2 point something. So 1 by e is going to be less than 1. It is, we are dividing 1 with some big number greater than 1. That's why it is going to be the less than 1. Now when it is less than 1, in that part is going to be decreasing. Is it clear?
Yes, sir. Got
Yes,
it.
sir.
So we have ex, which is increasing, and e to the power minus x, which is decreasing. Okay. Can we increase this? Can we do increase? Can we increase? Can we increase mean to say, can we do some sign here so that it will become increasing?
Minus sign, minus of x.
Yeah, minus of x we can do. So that's why I want e to the power minus x to the minus, we can say. So in that case, it is started increasing. So it will become increasing now. So how we can see in the graph? E power x is this one. And e to the power minus x is this one. And e to the power minus e to the power minus x is what? So whatever the output here you are getting, that will just reflect that side here. Sorry, this side, negative part, it will become negative. So how it is? The e power minus, sorry. So minus e power minus x, the graph of what it will be? Only, see, in that case, you are getting the output as the same. Only the sign will change here. Only the sign will change here. So this will be the graph e power minus x minus e to the power minus x, going to be the same. Whatever here is happening, here will come. Here will come. Here will come. The same thing as will happen. That means this is going to be the graph of minus e power minus x. Whatever the output you are getting. So now it is becoming increasing. So minus e to the power minus this is going to be increasing. So what is going to be here now? E power x is increasing, minus e power x is increasing. So if you add these two number, increasing number, if you add these two function, so still it will be increasing, right? So this function, see, here is what is happening. You have a function inside a function. So you have log, you have a big, some function inside, you have a smaller function, this one. And in this smaller function, we have separate function. As here, one by one, we are reaching, right? First, we reached e power x. Then we reached the e power minus x. Okay, then we slowly reach to the e power minus e to the power minus ex. And we try to graph. We have seen already properties of one by one, each one. Each of one, we have seen the property. And finally, we concluded that this is going to be the increasing function. Now we don't know the graph of this one. Now it is difficult to drawing this. But what we know, it is increasing. After making a part of this function, now we concluded this is going to be increasing. Okay. Now, once this is increasing, so
Sir, here
what
y equals to 0 is the asymptote.
y is equal to 0 is, yeah, it is asymptote. Y is equal to x means that x-axis is going to be asymptote, because we will never get the value. See, exponential will give ever 0 output. Ever this is true, a power x is equal to 0. For what value a power x is equal to 0? There is no value. That's why the x is generally asymptote for the exponential. As here it is happening. It is exponential. Why? X axis is exponential. Asymptote for the e power x. For the e power x, e to the power minus x, or e minus e to the power minus x. For all of them, as we are looking here. So what we did, we don't know the whole function, the whole this one. First, we attack on the inside portion, and inside portion again in the attacked in the smaller one. On one by one, we see it is very difficult to drawing this the graph of this one, getting the graph of this bigger one, not even the whole. But we know this one, and then after this one and the whole. So we don't know the graph, but one thing we reach that this number is going to, this function is actually increasing. Now the next thing is log. Now already you know log function is also increasing. So here is base is not defined here. I just wrote log in the bigger form. So you can think here is base 10, for example, as it is in log. So there are two notation. If it is in this fashion, x is given, that means log it is taken as log base 10. If it is not defined, otherwise it will surely, somebody will surely give. If it is not there, then you can assume this is with base 10. If it is in this fashion, that means here is base e, ln. So here is, I just wrote, I didn't give here anything. So that means this base is a. Now this base is a means a, sorry, base is 10. So 10 is greater than 1 already, in that case, log is increasing. So log is increasing, your input in the log. Sorry, here is. Your input in the log is also increasing, means larger number you are always will get for whatever, like if you assume x is equal to 3 give here in this portion, the output x is equal to 3 and x is equal to 5 will give, then in this inner function will give output, whatever the output will give, that is going to be greater than this output is greater than with respect to this one. And log is also give the greater, means log is also increasing. So final thing is the whole function is actually increasing, because log is increasing, inner function is increasing. So for the log, whatever the input you are giving in the increasing form, the log will also work like you are giving the bigger number. So log will also give the, in compare of increasing, we will say log is also increasing the whole function. Now the composition function is actually happening. So here is the two composition function, log and this inner function. So whole final thing is going to be increasing. So what we now know here, the whole log is actually increasing. Now you can tick here the options. So function our is increasing. Our function is increasing. And you know that if function is increasing, in that case, your generally function is 1. So this is going to be true. And if your function is 1, then that function is invertible. Then this option is going to be true for invertibility. Is it clear?
So can we? Yes, sir.
Hmm.
Can we use the graph Desmos or find the graph?
Yeah, let's see the graph of this,
Graphically,
how
can
the
we
graph
do
it
that?
is. Yeah, how the graph is.
Actually, sir, the last part I'm not getting. When you take x equals to 3 and 5.
Oh, that part is, I'm just explaining that how it is increasing. What do you mean by increasing? I said you are giving the input. If you want to compare, your input is 3, your input is 5. So let's say this is your gx. So if you compare, g3 is going to be whatever we don't know, because it is going to be e to the power 3 minus e to the power. We
It
don't
is
know what is the equation.
somewhere less than G5.
Yeah, but we know that it is increasing. So that means g3 is less than g5.
Yeah.
And our function is actually, the whole function is f. So if inner is this one, now you can give the 5, sorry, e3. E3 is going to be log inner e3 minus e minus 3. And here is log, sorry, e5 is going to, sorry, 5 is log e5 minus e minus 5. So as we know, this number is less than this number is less than this number, then log value also increasing. That's why the whole, so finally you can say f3 is less than f5. So mean to say the whole function is, our whole function is actually increasing. That's what I want to say from this one, this example, giving to the particular number, by giving to a particular number. So let's see that here. Let me remove this all. And this is log e to the power x minus e to the power minus x. So graph is this one. Is it clear? As y it is increasing, now it is 1 invertible all.
Yes, sir.
Can you tell me the domain of this function now? What is going to be domain for this function?
0 to infinity. Positive infinity.
0 to positive infinity.
Yeah.
See,
Sir,
we
it
know that
cannot be 0, right? Oh, 0 cannot, right? 0 should not be
0,
included.
0
Oh,
is not
yeah.
included. Open, you can say this is going to be.
Yeah, got it.
But this portion is also not exactly, we don't know. See, how you can say, see, we want, see, here is a negative. Here is negative. So how we can compare that when, till which number it is, see, the whole thing we want always positive. That means c power x minus e power minus x is should, we want always positive number. So till which number, till which input, it is always positive. This is one concern thing. So how we'll conclude that? So is this going to be in domain or some a and infinitive, where a is some a is greater than 0, maybe a is greater than 1, a 0.1 also, not exactly 0. So how we'll conclude that is this domain or is this domain? What is going to be a here? Because if you see now, let me show you the graph. What is happening in graph? After some part, this blue line is stopped now, not going to infinity. See this, not going to be ahead. After some part, this is going to be, it have stopped. So then you cannot say here is, this is going to be your domain. This minus infinity, sorry, 0 to, this part is fine, increasing, but this here is the problem. Because as you can see, after some part, it have stopped. Let's see that, till here it is. See, now it is bold. Till here it is here. So how we'll get here exactly the domain? So let's see. Let's see, for me it is new also. Let's see I'm able to reach there or not. So this is e power minus x. What it mean that? See, you have a power x or a power b and equal to a power c. Then what is b equal to c, you know. That means what is happening here? X is equal to minus x. What it mean that? This is going to be 2x is equal to 0. Oh. This imply x is equal to 0. Oh, one thing. Okay, just a minute. I just missing. Okay, let me see once again. So here is, this says when it is possible, when it is true, when e power x is greater than e power minus x. That means x is greater than minus x. And 2x is greater than 0. That means here is concluded x is greater than 0, but we didn't reach the exact point. Okay. This implies here, that's why we are not reaching exact number. Okay, why it is stopped, or either it is the
Also,
whole.
it should be less than 1. But how can we prove that?
No, so then I think this part is just stopped to telling you, okay, it is in kind of infinitive. I think, let me see with an example, another example. E power x, sorry, log x. Actually it is telling, I thought maybe it is, yeah, it is. So it is true actually, the domain is whole. Because while we are proving it, so see, we know that the domain of this one is log x is simply, in this Desmos is it is showing. So you can say in Desmos even not a whole part is showing. So you know the log is the domain of this log is actually this one. So in the Desmos, when I see that this thing is happening, so I thought maybe after some part it have stopped, but it's actually saying it is whole asymptote. When we have started looking to, when we have started investigating, we see that for x, where x is greater than 0, this function is always defined. That means always we get the domain of the whole function is actually this one. And in the Desmods, it is showing some part is stopped now. So I thought maybe after some value we cannot give that as input, but it is the whole actually. See, I thought because of it have stopped for the log also, log x. So domain of this final thing is actually open 0 to open infinity. Is it clear?
Sir,
Yes,
yes,
sir.
sir. Graph,
Yes.
sir.
And the
What is the
range will
graph
be the
for
whole real
log
line.
x, sir?
Yeah, range is the whole real.
Can you
Sorry,
explain the
somebody
log
was
x
saying
graph,
some
sir?
graph of log x.
Yes, sir. What is the output of that? How you can verify for the value of x? What will be the value of y for log x? The graph. In the
Log
graph.
value is exactly, see, log value. That's why we used to like in the mathematics here not given the log value, log base 2 to the power 5. Is my pen? Just a minute. Just a minute.
Yes, sir.
Okay. So log base 10 to the 5 value is not, we cannot directly evaluate. It is usually given. That's why that there is in books and all, whenever there is a logarithmic chapter in the books, in the last, if you see that the log value, such kind of log value is given generally. Log base 10, log value is given. So not exact value you can find, but yeah, the graph, from the graph you can conclude. So from log with base 10 or for any base ax, a greater than 1, in that case the graph of log is this one, where y-axis has a asymptote. This is the graph for log. Let's do one example.
Oh, base 10, sir.
Yeah, base 10 or a greater than any case. A greater than 1. In that case, this is the graph. So it is true for the base 10 also. For this one, the graph is very similar to this one.
Right.
Okay. So let's do one domain of the. Let's do one example. Then we'll end the session. Domain. Starting it is even. Like here, this one. Let me write this. This is log and base 10. So I'm just erasing it because this is itself convincing that this is base 10. The whole square minus 8 log plus 15. This is our function fx, and we want to find the domain of this one. So see that so how we'll solve this? Again, you have some function inside function. So how we'll solve this such kind of problem? So we know for the log.
The values of x.
So values of x will conclude, but let's do in the part wise as here. Again, we'll make some part and we'll try to do. Okay. So,
Right, sir. Right. We'll do that.
so as here, this is this log is out and this is the whole value of inside we want as a log value. That means the whole person, this whole portion, this is log x whole square minus 8 log x plus 15 should greater than 0, strictly greater than 0.
Right.
This should happen. Then we are able to take the value as log. So if you want this portion as positive, when it will be positive? So one thing is,
In minus 8 log x should be.
so
Log x whole square will always.
if it is negative, minus 8 log x is negative, then the whole thing become the positive. Because of minus in here, it is going to be positive, whole thing is positive. But we want exactly x, in which portion this is going to be your whole thing will give the positive number. So here one thing is need to note here. If we assume log x as y, then it is this. This is a quadratic function, right?
Right.
So it is actually, this expression is a quadratic function in the form of log. And if you have this one, so when this portion is, so if you have quadratic, can we, now we can let's back to our quadratic portion, quadratic function. Okay.
5 and 3, yeah.
So you can fraction it. So yeah, you can fraction this one is 3, 5, and this 5 you will get 8 here. So you can fraction, you can make it like this, right? This is going to be this one,
Y is equal to 3 and 5.
right?
Yes.
This is correct. Now, once you have this one,
Yes, sir.
now you can conclude when this function is, the whole thing is going to be positive. When it is positive, see, now you can make a part, this one and this one. You have to multiply, you need to multiply these two number, this one and this one. So when this will happen, separately we have to investigate. So how we can, when this portion is positive, when y is greater than 3, right? And
Right.
and y is greater than 5. In that case, the whole thing is going to be positive, because this is going to be now give a, if y is greater than 3, okay, positive number, y greater than 5, positive, or finally you can say y greater than 5, because y greater than 3 and y greater than 5 means you want 5, y greater than 5, right? So if it is y greater than 5, or sorry, y greater than, no, y greater than 5. If y greater than 3, let's say 3, y is equal to, I am taking 4. So what is going to be? This is 1 and this is minus 1. So it will become minus 1 finally. So if y is greater than 5, then whole expression is going to be positive. That means this one is going to be positive. So y square minus 8y plus 15 is positive when y greater than 5. This is fine.
Yes, sir.
Now, let's investigate further. If y is less than 3 and y is also less than 5, so not even 5, if it is, suppose y is less than 3, okay, and y is greater than, in this portion I mean to say, can you think about this portion 3 to 5? In this portion, what is happening? 3 interval 3 to 5. What is happening in this interval? In this interval, this expression is actually negative.
Decreasing. Yeah.
Sorry. In this portion, it is
Decreasing.
negative. Yeah. because if you can take 4 as example in between, and when you are substituting, we are already investigated, it's give negative. So in this interval, it is going to be negative. So here you can write that expression is negative in this interval. Okay. And if it is y is finally less than 3, then this is negative, and final thing is give positive. That means when this is greater than 0, when y is less than 3. So y greater than 5 in that case positive, and y less than 3 in that case is positive. And we don't want y is equal to 3 and y is equal to 5 because we have y as a log. So, okay, let's include that. I think, yeah, because y as a log you are taking, so y value can be 0 also. Log value can 0 at 1. Log at 1 is 0. So you can, let's include that 3 and 5. So that means this portion is okay, but we want this thing. We want this one, but the whole expression we don't want 0 because the whole expression is actually in the log. That's why we are investigating here the whole expression in the log. So at 5, what is happening? Value is this expression is going to be 0. At 5, this expression is going to be 0.
Yes.
Okay, sir.
So that's why we don't want that. But okay, just a minute. This expression is going to be 0. Okay. So that means y minus 3 and y minus 5 is 0 when y is equal to 3 and y is equal to 5. So yeah, at y is equal to 3 and y is equal to 5, it is going to be 0. Fine. So we don't want that. The whole expression is going to be 0. So we don't want at 3 and 5. So we have to neglect that 3 and 5. We have to remove equal y is equal to 5 and 3. So only these two portion we want, this one and this one. Now, if y is greater than, so now, so see, y is greater than 5, that means our log x is greater than 5. Y is actually log x we have assumed. That means now let's find the x value from here. So this is going to be 10 to the power, our base is 10. So 10 to the power 5, this the same will happen x. Okay. This inequality still will remain. So already you know that if a to the power b is equal to m, then in that case, if you take the log, this will become base will become base, and this will become m, and this power will go this side. So that's why, and from if it is in this fashion, this is if and only if condition. From here you can conclude if in this fashion you can back to here. So here is same. This will come to the power and this will go to here. So the inequality is still remain. That means this is one thing, and another thing, y is less than 3. That means log x is less than 3. That means 10 to the power 3 less than x. So finally we concluded that if it is when x is greater than 10 to the power 3 and x is less than, here is x is less than 10 to the, in this portion, I just inverted this. In this portion, our function will behave nicely. There is no issue with this. So let's see that how our graph, how our domain we can. I think, yeah. So we want in the form of this one. So let's make it here. In the 0 to infinity, we need to expand it here. So what is happening here? X is less than 10 to the power 5 and greater than 10 to the power 3. So x is minus infinity to 10 to the power 5, we can make union in this portion, and x is greater than 10 to the power 3 to infinity, we can use as here. No, so I think I am missing something, that's why it is going wrong. Okay, I'm missing something.
So if x is minus value, then it should be the value will be minus on the y minus 3 and
That's
y minus 5.
sorry.
So y minus 3 and y minus 5 equals 0.
Y minus 3 equal to 0 and y minus 5 is 0. Yes. Why we are not including this 3 and 5? No, can you repeat again, please? I didn't get. I'm not getting what you're saying.
So right side root we take y minus 3 into y minus 5 equals 0.
This one.
If we take y minus value, it will come into minus value.
If we take y minus value, minus 5, is that? No, I'm not getting, like you are asking it out or are inferring something from here?
I inform.
So yeah, if it is less than y is less than 3, then this is going to be positive. Because
Yes,
this
sir,
is
but-
going to be negative. So say any negative number we included here.
So when we are replacing y with log x, the left side, sir, here 10 to the power of 5, the sign is greater than or it should be less than?
Yeah, we
X,
have to, yeah. So let's investigate
less than or
actually. We have
equal?
to investigate. Yeah, that's why it is, that's why we confused here. So we have to investigate
Yes.
here what is happening here.
Yes.
So you have log x is equal to 5, greater than 5. What is going to be in that case? So how we will conclude this one? Is this inequality will change or still remain?
X should be greater than 10 to the power of 5.
So let's see that. So we can easily do that. If we have this one, you know that if 3 is greater than 5, sorry, 5 is greater than 3. So if you take 2 to the power 3, still 2 to the power 5, the inequality will be same because 2 to the power 3 is 8 and 2 to the power 5 is 32, I think. So when you are taking the base, you are taking as a power, the inequality still remains same. So it is actually true for any greater than 1 case. The same case will happen here. You can take both sides as power to that expression. Right? It will not affect. And this is actually x because it will get power, 10 to the power log base 10 to the power x. This is x and this is 10 to the power. So actually inequality will not affect. Inequality will not affect. Okay.
The above line, but we have taken x as less than 10. Just above the box.
I took x is less than 5.
Yeah, less than 10.
This one. Okay, no. So it is fine. So what is happening now here? So we have concluded that y is greater than 5 and y is less than 3. So our y is actually in this portion. Minus 0 to 3 here. Okay, union. Our y we want in this portion 5 to infinity. We want, right? We want in this portion our y.
Right.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Our y is actually, yeah, that this is fine, but we didn't make a clear thing. So our y in this portion we want. Now our 3 is deciding for y. So finally, what is 3 is deciding y means y is actually log. So y is actually log 10. Sorry, log base 10x. And we concluded that if it is log with any number, let's say m is there, in that case, this is going to be 10 to the power m, and this is x. So from here, you can finally conclude that 0 to 10 to the power 3 in this portion, the whole domain is going to be 10 to the power 5 and infinity. Now it is fine.
Sir.
Yes, sir.
So while looking this process, we can see our domain slowly. Yeah, I see. I also don't know how to solve, but yeah, I'm slowly I'm sitting here with you and solving so that you can learn, and I also myself learning. Okay, whatever I have property. Okay, so this is all about, I hope many things have clear regarding the log. Is it clear to all of you? How many of you
Sir.
are here? 17. Okay. Yeah.
But still lot is there to be learned and practiced. Then only we can understand more. Logarithms.
Once the graph and the domain is clear, you can do anything with the expression or whatever you have. Make sure that domain is what is, and if you are able to somehow whatever you have property, many times use one increasing decreasing to infer something. As here we are trying to investigate, right? Increasing and decreasing, we are try to investigating something we are reaching. So this is all about. Please let me know anyone have doubt. Or it's 9 already, so we can now close the session one by one. So if anyone have doubt, please let me know. Okay. No one. So can we close the session?
Yes, sir.
Okay, because almost I have covered everything in the week 6, and only solving the equation part is remain. So already many times I have used the properties. Using the properties of log, usually we used to solve the equation of the exponential logarithmic equation or exponential equation. So we have more toughest thing we have already investigated. Slowly you can investigate for the equations also using the property. You can easily do. In the property, usually the changing the base, and these two properties very important while solving the equation. If this 5 property, if you use many time, it will easily done. Many times, generally this one and this one. This is very important. Generally, what the people used to give, they give some equation like this: x to the power 5b plus y to the power 5 c, some equation equal to 0. Now we have to do whatever we want to use property. See that in each case our base is same. So anyhow we have to make the base same. So how will make the same base? Using these two property, either this one or this one, or even this one. We can, using these 3 things, 4 things, we will try to make the same base. And once we got the same base, then you can do all whatever this one, or adding them or multiplying them, whatever. Using these two property, you can solve. Okay, let me mute. So this is all about. Now I'm going to end the session. So I want to say these, actually these two are very important. This one is very time I used to be like many times they used to give a big expression. They used to be like this sometime, log 32 and plus log 16. Now see that base are different. Let's say it is the expression is given, let's say C and B here. Some expression is given. See, the base is different, but we can make the same base. How we can make this 32 can be written 2 to the power 5, and this 16 can be written 2 to the power 4. Now we can use this property. If it is a power a to the power something, you can send 1 by n. Now send 2 ahead and make the same base. Right? So this one is many times I used to generally see how we'll make the same base. Is it clear?
Yes, sir, clear, sir.
That's all for today. Thank you so much. And I think week 6 deadline is on Wednesday. So before that, we have one session on Sunday, which will be taken by Subhasis. And there is one session on Monday, which is going to be Solvita session. So yesterday, anyone have attended the Solvita session?
No, sir.
No, it is streamed. Please see there. It is on YouTube.
I attend, sir. I attended.
So how was that session?
It was good. Just like all of these sessions, I attend before.
Yeah, because see, that session is taken by TAs.
Yeah.
So I thought maybe that's why we want some feedback. How was that? So we have collected in the G form.
No, anything not is special there. It's just similar, like.
Very similar, no? Because in Solvitas, generally we used to sit and solve some question. So hope that was, yeah. So the next Monday session, now the Solvitas session usually take by.
Do week 3 deadlines are extended anymore?
Week 3, no, week
Oh,
5.
sorry, week 5.
No, it is not extending till today is only the last day. Already it is extended from 1 through 3. If it is you want to extend, then they will inform you. You will get in if it is extended, but I'm not. No, generally if it is there, then I will surely get. Either if it in a daytime, you'll get a mail. So be careful with the today's announcement. See that many times if there is announcement for extending the date. Yeah. But I'm not sure the date will extend. If it is there as technical issue, then it may, but because of quiz or for any other reason, it is not going to be extended.
Sir, one more thing, is this our foundation level going on?
Foundation level means what? Foundation level?
We are on our foundation level, right?
This is a foundation level course.
But still we don't get the form to select the courses. That's why I'm asking.
So you are enrolled already, or you gave the qualifier? And
I just gave the qualified on 26 Feb and qualified.
And qualified, okay. So I don't know, you'll get to choose, or it's already going, because math stat. Once you have given the qualifier, then you can choose the math stat or math English, math CT, or other whatever the combinations are there. We'll get. I don't know. Please be careful with the mail. Okay. Yeah. And everything just believe on the mail from the ITM only, not from other part. If it is authenticated generally from the IIT, then you believe. Otherwise, don't believe or other, because many scam can happen. Okay.
Sir, but we can select any combination, right?
Yeah, I mean math, stat, CT, English, you can select any combination.
Okay.
Okay. Thank you so much. Have a nice day. Now I'm going to end the session. Thank you so much.
Thank you, sir. Thank you very much.
Thank you, sir.
Thank you, sir.